Hello everyone. Today I'm going to start creating a physics engine. And I'm doing this with the purpose of learning, of education. I want to understand better how they work. And for me, I'm really interested in creating one from scratch just to see how it goes. I believe I can do it. I have high hopes, but I've never actually created a full physics engine. I did a little bit of prototyping, so I think it's something I can accomplish. I'm pretty sure. But if this sounds like something that interests you, let's go ahead and give it a shot. Let's see what we can do. I will be using C# and the .NET framework, as well as monogame to get the graphics on the screen and have user input, and also a three-dimensional camera that allows us to zoom in and out of the scene. Now, this physics engine is going to be completely two-dimensional, but I will be using the camera to zoom in and out of the scene. I will be using the metric system, so everything will be in meters and kilograms. As far as the coordinate system goes, I will be using positive x is to the right, positive y is up. And then when we do use z coordinates, positive z will be pointing out of the screen and negative z will be pointing into the screen. All right. So if this sounds like something that interests you and you want to give it a shot, maybe we can learn something together. Let's go ahead and get started. So here I am. I'm in Visual Studio. I have a basic game window set up. And I'm also using the flat library that I've created, which is over here. And the flat library is an extension library that I created for monogame that'll make two-dimensional game programming and prototyping really easy. It gives us access to a camera that we can use to zoom in and out of the screen. It gives us shape drawing and statistical drawing really quickly. And also user input, makes user input a little bit easier. So if you'd like to watch how that code was created, all of the videos are freely available on my channel. You can go back and pick whichever subject interests you, but also the code is going to be freely available on GitHub, so you can just download it as well if you like. So let's get started. I'm going to call this physics engine the flat physics, meaning it's all going to take place on a two-dimensional plane. So kind of a flat area. And I'm going to make a new library. So we're going to add a project. So let's add a new project. This is going to be a class library. Let's go next here. Go ahead and pick the spot we want to install that. And I'm going to call this flat physics. All right. And let's go ahead and hit create. Okay, here we are. We have an empty flat physics library. It gave us a class 1 CS. We're going to go ahead and delete that as we will not be using any code. We'll be making all of our own code from scratch. And now the very first thing I would like to do is create a vector class. And the vector class is going to have an X and a Y component and allow us to pretty much represent anything on the two-dimensional grid. And in reality, the vector class is going to be the building block is what's looking like, the building block of most everything else as far as any of the math goes, how we represent everything on the screen. The vector 2 is going to be an integral part of all of that. And so I need the vector class to be first of all, very lightweight, and it's actually not going to be a class. I'm going to make it a struct, but I need it to be very lightweight, meaning the memory that it uses is going to be the bare minimum, okay? And then I also need to be very high performing, meaning that whenever I'm working on a vector 2, I need it to be just as fast as if I was working on 2 floating point values. So let's go ahead and add our new vector struct. We're going to make a new item, and I'm going to call this the flat vector. And that's pretty much going to be my naming convention for everything in this library, is I'll probably preface it with flat. And this is not going to be a class, but this will be a struct. And in fact, we are going to make this a read-only struct. And so we need an X and a Y, so we'll have 2 read-only floats. First one will be an X, and the next one will be a Y. Okay, and then we can just make the constructor here. We'll pass it an X and a Y, and then just make the assignment. Okay. Now, I do want to do a little bit of testing here because, I need this to be really fast. I need, like, if I'm doing vector addition, I need it to be just as fast as if I was just adding two floating point values to two other floating point values. And so let's go ahead and do some testing. I'm going to I'm going to overload the addition operator. And so that's going to return a flat vector. And that will be a addition operator. And we're going to pass in two flat vectors. And I'm just going to call them A and B. And then it's going to be really short and sweet. We're just going to return a new flat vector that is the addition of the components of each one of the flat vectors that we passed in here. All right, so the way that looks is just going to be the x component of A plus the x component of B. And then the y component of A plus the y component of B. Okay, so I'm hoping by making it really short and sweet like this, there's nothing else going on. All we're doing is adding two floating point values. I'm hoping this will be just as fast as if we were just adding floating point values without this structure around it. So let's go in here. We don't actually have access to the flat physics library in our game yet. So I'm going to go into the game class. And so here's our main mono game. Here's the constructor. All I'm doing here is I'm creating the graphics. I'm telling it I want a fixed time step, and then I tell it how fast or how often that time step is going to happen. And so right here I have a value called updates per second. I tell it I want 60 updates per second, and then it will target that as the time or the number of updates that it'll do. Okay. Here's my initialization code. These are just these are helper classes that will allow us to get things on the screen, as well as a camera so we can view stuff. Here's our update function. This is where all of our physics is going to happen, but right now I just have keyboard and mouse input ready to go. If I press escape, it will exit. If I press the A key, it'll allow me to zoom in. If I press the Z key, it'll allow me to zoom out of the scene. Okay, so it will be a two-dimensional scene, but the camera is positioned in 3 dimensions, so I can zoom in and out. And then finally, I have the draw here, which will allow me to draw shapes. Okay, and the library, the flat library, has a screen class, which allows me to create a screen that I draw to that will keep the same aspect ratio and resolution, but scale to fit whatever window resolution the user currently has. And then I have a shape batcher here. This is where we're going to do all of our drawing as far as our physics goes. And in here, I can do stuff like draw a circle. And you have two options. You can draw a circle or draw a circle filled. If you do draw a circle, it's just going to draw a circle outline. And we can go ahead and let's just put one at the origin of 0, 0, radius of 32. And the number of points will determine how many points it uses to draw the circle. So the more points you have, the more round it's going to look. So let's just pick 32 for that one. And the color will just be white for now. And let's go ahead and run this just to make sure everything works. Okay, there we are. So there's the circle I drew. Now we've zoomed in. I have the camera zoomed in quite a bit. That's why 32 looks so large. But I can zoom out. So there's basically we're zoomed all the way out. Now 1 meter is going to be equal to 1 floating point unit. And so I'm going to want to zoom in. Otherwise, 1 meter would look really tiny, right, on the screen. So if I'm zoomed out like this, 1 unit would look really small. But if I zoom in, we'll be able to see 1 unit better, okay? And we can kind of choose how we want it to look by zooming in and out, all right? So there's that. That looks like it's all working just right. Let's go ahead and write some test code here. I'm just going to put this in the initialization function, and before everything is initialized, what I would like to do is just loop through and do a bunch of floating point operations. So I'm going to loop a bunch of times, and let's just, how about 1,000,000 times? We're going to loop 1,000,000 times, and we're going to do 2 floating point operations. So I'm going to have an x1, which I'm just setting to some random values here, and I'm going to have a y1, which I'm going to do the same thing. Okay, and then we're going to have an x2, which will also be random, and a y2, which will also be another random value. Okay, and let's just, maybe we can make this 0.01, and then we'll start this one at 0.5. Okay, so a bunch of random floating point values, and we're just going to increment them by the other value. And before I do any more, let's make a stopwatch. So we're going to make a stopwatch here to do the testing for how much time it takes. We're going to start the watch at the beginning, and let's stop the watch. Let's stop the watch at the end here. There we go. Okay, so, oops, get rid of that 0. Okay, so now it's going to loop 1,000,000 times, and it's going to do this floating point operation. It's going to do floating point adds twice every time it loops. Representing a vector, right? So every time we add a vector, we're adding 2 floating point values. And I want to, you know what, I'm actually going to make this a console application. So we're going into properties here of our application, and the output type, I'm going to make this a console application, so then I can see some debugging information if I want to. I can send it to the console window. And so from there, I can tell the console that I want to write, first of all, let's write the results of our addition operation. Okay. And so that'll look like this. X1 will be the first result, and then Y1 will be the other result. And then let's write out the amount of time it took. So the time will be this. I need to put the operator over there. Okay. And the time will be the watch elapsed, and I want to get the total milliseconds. Okay, so that'll just tell us how many milliseconds it took. And then let's tell the console that we want to read a key just to pause until we are ready to continue. All right, so I'm going to switch this to release mode so we get all of the optimizations going, and let's run it, and let's just see how long it takes to do this operation. Okay, so 1,000,000 times is telling me that to do, well, it's actually 2 floating point operations, floating point adds, 1,000,000 times took 0.7091 milliseconds. Okay, so, and that sounds about right. So if I run the numbers here, so 0.7091 divided by 1,000,000, that'll tell me how long on average it took to do one. And then if I want to know how many milliseconds it takes, let's see, if I want to know how many of those I can do in a millisecond, I would just take the inverse. So this is telling me that in a millisecond, I can do 1.4 million adds, floating point adds twice, because there's 2 adds in every loop. So if I multiply that by 2, it's telling me that that's, my computer can do 2.8 million adds per millisecond. And then if I want to get how many adds I can do per second, I just multiply that by 1,000. And so it's saying that I can do 2.8 billion floating point adds per second. Okay, and so that sounds exactly right. And so, but in reality, this is the only number that I really care about. So I want to get this same number when I'm using vectors. So let's go ahead and now do this same operation, but with vectors. So we'll create a flat vector. Oh, and we don't have access to the flat vector. So let's, okay, so over here in our project, under dependencies, we need to add a project reference. And we're going to tell it we want to add the flat physics. All right. And then we need to bring in the flat physics namespace. So there's flat physics. All right, and now we should have access to the flat vector. I'm just going to call that A, and it's going to be equal to x1 and y1, just so we're using the same values. And then flat vector B is going to be equal to y2 and, or x2 and y2. Okay, so we're using the same values. It's just now we have them encapsulated inside these structs. And instead of adding them individually like this, now we are just going to increment A by B. And if I wrote this correctly, we should get the same performance. let's go ahead and, oh, and actually I want to write out what the results are. So let's write line. And instead of x1 and x2, we are going to actually put a x and then a y. Okay, and we'll get rid of that one for now. We don't need that one. And okay, we're in release mode, so let's give it a shot. Let's see what happens. And you know, that looks like exactly the same amount of time. It doesn't look like any variance at all. Okay, there we go. There's a little bit there. So perfect. So we know that our flat vector is fast, it's lightweight, it's efficient, and lightweight, it only uses 2 floating point values. We don't have anything else in there. So we can go ahead and finish it up here. Let's finish our flat vector. And basically, we want to just add all the operations that we might be using. All right, so we have addition already. We want subtraction now. And when you're doing vector math, there's really only a few things that you need for a physics engine. You're going to need addition, subtraction, you're going to need multiplication, and you're going to need division. Those are the basic operations. But on top of that, there's a few other functions that we're going to want to create, and we'll make a math library for that, for vector math. But there's really not a lot of vector math that you need to know. So once you learn these basic concepts, like how to add and subtract vectors, how to multiply vectors by scalars, how to divide vectors by scalars, there's just a few more functions you're going to want to know. First of all, you're going to want to know how do you get the length of a vector. You're going to want to know how do you get the distance between two points in space. You're going to want to know how to normalize vectors. And then you're also going to want to know something called the dot product of two vectors and then the cross product of two vectors. And then I believe once you know those things, at least when I was investigating how all this works, those were pretty much that's all of the math that you would need to know, right? Once you know that math, you've got it. There's no other math that you need to know. Now, I might be oversimplifying that a little bit. There's still physics math you need to know. But as far as vector math goes, that's pretty much it. I can't think of anything or any other vector math that you would need to know to create your physics engine. So we have the 4 basic operations, and I think there are 4 or 5 more functions on top of that you want to know. But once you know that, I think you're pretty much good to go. And we'll talk about how all that works. Right now, let's just make the basic operators for vectors. So the next one is going to be subtraction. So let's subtract 2 vectors. And then we need to do multiplication and division. So let's have we're going to return a flat vector. This is going to be multiplication. And when we're multiplying, what we're going to do is we're going to multiply a flat vector by a scalar. I'm not going to multiply 2 flat vectors together. I haven't seen any use for that. So this is going to be the flat vector times the floating point scalar. And we want to make this really lightweight. We don't want to have any other code in here other than just the multiplication or the addition or subtraction. It's got to be very lightweight, so then the compiler can actually optimize it and make it run really fast, just as if it was working on floating point values. Okay, so we're going to take the x component, multiply it by the scalar, and then the y component and multiply it by the scalar as well. And then let's just do the same thing for division. So when we divide by a scalar, we're just going to hit divide like that. And there we go. We have all of the operations. And you know what? Actually, there's one more. We do want to be able to negate a vector or to change the sign, or to, I guess, change the sign to the opposite. And I'll just put that one here underneath the subtraction operator. So it's going to return a flat vector, and it's just going to take as an argument 1 vector, and we're just going to return a new vector with the signs being the opposite. So it'll be a negative x and a negative y. Okay, and I think that's all the basic operations we need right there. And what else? Okay, and then finally, just to wrap this whole thing up, let's go ahead and let's make a static 0 vector, so we can call that if we ever need to. So this would be a static read-only vector. And I'm going to call this 0, and that will just be 0 components like that. And then finally, let's wrap up our struct by making some equal, or we need to make some, I want to make the ability to get the hash code and to get a string representation of the vector, and also to check if two vectors are equal. And so let's go ahead and make a function for equality, and we're going to pass in another flat vector. And actually, instead of v, I'm going to call this the other. And again, this is going to be very lightweight. We're just going to return if this x is equal to the other x, and this y is equal to the other y. And if that's true, then they are equal. If not, they are not. Let's go ahead and override the basic other equals function here. First of all, we want to test to see if this object is a flat vector. And I'm going to call this other. So we're doing some... so what I'm doing here is I'm actually doing some, I guess it's called pattern matching. I'm trying to remember what they call that. But I'm determining if this is a flat vector. And if it is, I'm going to cast it into this variable as a flat vector so I can use it. And then if it is, I'm just going to call this function and see if they're equal. All right, so let's call the equal function. And we're going to pass in our other vector. And so... and we actually need to return the results of that. Okay, so if it is a flat vector, we're going to check to see if they're equal and return the value. If it's not a flat vector, then we're just always going to return false. So there's our equals. Let's just go ahead and override the rest of this. So we will override the hash code. And I'm just going to make this nice and simple. No reason to get complicated. We're going to create a new anonymous type. Okay, oops, not a new integer. This will be a new anonymous type. And for the type, we're going to use the x and y from this struct. And then we're just going to get the hash code of that created anonymous type. So we're kind of letting C# do all the work here, right? We just create an anonymous type and get the hash code that's created from that. That'll just simply be the x and y values. So it'll be x and y. I think that's all I want. Maybe I can I could put x like that, and I could put y like that. Sure, I'll leave it like that for now. Maybe I don't even need to do that. Maybe I can just put parentheses around it, but anyway, okay, that's good enough for now. It looks like this class, or this structure, is looking really good. I know it's high performance. We just tested that. That's it for this video. We have the basic building block, which is the vector class. The struct is high performance, it's very lightweight, and I think we're good to go with the rest of the engine.